Hello, in this video, we're going to delve into the simulation of a wastewater treatment system that has gained a lot of popularity. Sequencing batch reactors, or SBRs. Batch systems like SBRs are a very efficient technology. A great example of its large-scale application is the Tlaxcala wastewater treatment plant, which has the capacity to treat up to 700 liters per second. This plant is not only a benchmark in Mexico for its size, but also for its focus on environmental education, with a park and an immersion center for visitors. Inspired by this type of facility, we are going to use the GPSX simulator to model the operation of an SBR system. Unlike the continuous flow systems, the configuration of an SBR system presents an interesting challenge. How do we handle a continuous inflow in reactors that operate in batches or discontinuously? The key lies in the correct flow configuration to ensure that while one reactor is in its filling phase, the others are completing the other stages of the treatment cycle, thus guaranteeing uninterrupted operation. In our model, if we right-click on one of the SBR reactors, we can access the cycle configuration. By default, the software offers us 10 phases, but we can adjust them to our needs. In this case, we have programmed 5 phases. The first, lasting 1 hour, with regime 1, which means mixing and aeration. A second phase continues for 3 hours with this same mixing and aeration regime, and we move on to a third phase of half an hour, but in regime 0, meaning it has neither mixing nor aeration. We continue with a fourth phase of 1 hour under these same conditions, and a fifth phase of 30 minutes, also in regime 0. The complete cycle lasts 6 hours, which means each reactor will complete 4 cycles per day. Now, how do we distribute the wastewater? One way is to use a splitter or flow divider, which has a configuration menu. In the configuration, we set it to time-based mode, so that the flow changes from one reactor to another every 2 hours. That is, every 2 hours, the entire inflow will be rotated among the 3 outlets. Regarding the reactor's flow control, it is vital to define at least the minimum operating volume. In this model, or in this example, it is 2,523 cubic meters, with an inflow of 25,380 cubic meters per day, and a filling time of 2 hours. Each reactor receives 2,115 cubic meters per cycle in this time. Therefore, the useful volume of the reactor is the sum of the minimum volume of 2,523 cubic meters plus the filling or working volume of 2,115 cubic meters. This brings us to a critical point, the decanting flow rate. If filling takes 2 hours, the decanting must be faster. In our case, we programmed it for 1 hour, which implies a decanting flow rate of 59,738 cubic meters per day, a value that is configured in the flow rating per phase menu. An incorrect configuration of these flows can lead to errors. For example, if the decanting begins before the filling is finished, the model will yield inconsistent results and the operating profile will be erratic. As we can see in this graph, correct synchronization is essential. Now we are going to run the dynamic simulation for 10 days to observe the system's behavior. We can analyze the reactor's flow balance. The black line represents the filling, and the red, the decanting, showing coordinated cycles. The tank volume in green increases during filling and decreases during decanting, as expected. Finally, the results at the discharge before disinfection show us the quality of the effluent. As you can see, simulating SBR systems in GPSX is a very powerful tool, but it requires detailed configuration and a clear understanding of the hydraulics and the process operation. I hope this video has been very useful for you to better understand how to model SBR reactors in this particular software. If you have any questions, don't hesitate to leave them in the comments, and thank you very much.